Hi, I'm Tyler, and I'm going to be giving this talk on the tight time-space trade-offs for the decisional Diffie-Hellman problem for STOC 2024. This work was done mainly at NYU Shanghai, and that's our main affiliation, and it was done with Ekshima, myself, Xiao Guo, Jie Xie, and Yuping Ye. So first I'm going to start with just some background information about the problem that we're actually going to address, and we're going to start with Diffie-Hellman key exchange, because that's sort of the fundamental reason why we want to study this Diffie-Hellman problem, is because there is this key exchange protocol that it is meant to model. And the idea behind key exchange in general is that two parties are going to agree on some private key over a public channel. That is, they're able to agree on a key which they can use, for instance, for symmetric encryption, but the messages which they send are able to be eavesdropped on, and still the private key is meant to be shared only between the two parties participating in the key exchange protocol. And one of the good things about Diffie-Hellman key exchange, which is a key exchange protocol which was introduced in 1976 and is still in wide use today on the internet and all over the place, is that it's a non-interactive protocol. So that means that each party is going to send only a single message back and forth. The basic setting for Diffie-Hellman key exchange is there's a shared group. The group is cyclic, so it has a generator, which is denoted little g here, and it has order n. And n in this case we're going to take as just being a prime number. And in practice it generally is a prime number. And so the way that the protocol is going to work is that each party is going to take the generator g. They're going to generate a private integer, which is known only to themselves. Then they're going to exchange messages. A is going to send g to the x, B is going to send g to the y, and then given that message that they received and their own knowledge, or the integer that is private to themselves, they're both going to be able to compute g to the xy. And that's going to be the private key that they're going to then use for symmetric encryption or whatever other purposes. The main idea is that A, that key is going to be hard to recover given only g to the x and g to the y, but neither the integer x nor the integer y, and separately that key is going to be close to a random key, because in symmetric encryption generally that's what we want, is we want a uniformly random key. So in order to actually analyze this protocol, what we're going to do is we're going to introduce something called the generic group model. The goal is to obscure the group structure so that instead of analyzing a specific instance of the protocol, for instance, for some specific group G, we're going to answer the security of the protocol with regard to any possible group G. And the way that this is going to work is we're effectively going to generate some labeling function which is able to say, okay, instead of G, I'm going to give you some sigma 1, where sigma 1 is just some random label that I've applied to G. And instead of G2, I'm going to give you sigma 2, right? So effectively what we're doing is we're taking these group elements and we're hiding them behind some random labels that are not known to the algorithms themselves. So, I've written here, I've said g to the x is going to be the same thing as sigma x, where sigma x is some random bit string that is unknown. Well, okay, so you have a random bit string that's unknown. What can you do? Well, the one thing that you can actually do on a generic group is going to be the group operation, right? So notice if I multiply g to the x times g to the y, for any group g, I'm going to get g to the x plus y. And so what I'm allowing you to do here is, okay, I'm going to give you this oracle, and when you give this oracle sigma x and sigma y, it's going to tell you sigma x plus y, where, of course, sigma x plus y is just going to be another random label that doesn't actually expose any information about g to the x plus y. And so through this model, what we're able to basically study is, well, how difficult is it to break this key exchange protocol if all I have access to is these random labels and this group operation? And more than that, I'm able to quantify that difficulty by quantifying the number of group operations that it would take. That's sort of the backup and the model that we're going to look at. And so the first thing that we're going to introduce in that model is the actual problem that we're going to study, which is the decisional Diffie-Hellman problem, or DDH for short. In this problem, I'm going to give you g, I'm going to give you g to the x, I'm going to give you g to the y, and then I'm either going to give you g to the xy or g to the z, where z is a separate uniform random integer, and your goal is to tell me, did I give you g to the x or did I give you g to the z? This is sort of looking at that pseudo-randomness of that key that I'm actually agreeing on, because as I said before, we hope that g to the xy looks like, in some sense, a uniform random string. And so the goal here is, well, how similar is it to a uniform random string? Exactly how difficult is it to tell the difference between the key that we agreed on and a uniform random string? And that's going to be related to what we call the discrete log problem. In this problem, instead of looking at g to the x, g to the y, and g to the xy, we're given only g, the generator, and g to the x, where x is some uniform integer. And the goal that we're tasked with doing is we're tasked with actually finding x. You can think of this as you're eavesdropping in Diffie-Hellman, you hear one of the messages that's sent, and you're trying to figure out, oh, well, what actual hidden information does that party have to generate this message? Additionally, there's this third problem called square DDH. In square DDH, instead of giving you g to the xy, I take g to the x, I square x, and I either give you g to the x squared, or I give you g to the y, where y is uniform random integer. And so one of the main questions that we're going to ask when we're looking at, what is the new thing that we've proved is, how do these three problems relate? And specifically, how do they relate in the generic group model? So as you can see here, all I've done is I've said, okay, in the original problem, I'm going to give you g to the x. Well, now I'm going to give you sigma x, where that's a random label. The goal of the problem is still the same. I'm supposed to tell the difference between sigma xy and sigma z. The only difference is now all I'm allowed to do is to perform those generic group operations instead of being able to look at the actual values of the group elements themselves. And so one of the things that's going to be interesting in this case is noticing that both the DDH problem and the square DDH problem can be solved by solving the discrete log once. This is somewhat intuitive if you think about the Diffie-Hellman key exchange protocol, where if I'm able to recover the view of any one of the two parties and I know the message that was sent to that party, I can trivially compute the key that both parties agreed upon because I have the same view as one of the parties themselves. So specifically here, how am I actually going to do this? Well, on the left and right, you see both a DDH tuple and a square DDH tuple. The first thing I'm going to do is I'm going to solve the discrete log. I'm going to find the value of x. The next thing I'm going to do is I'm going to compute either g to the xy or g to the x squared. The next thing I'm going to do is I'm going to compute either g to the xy or g to the x squared. Finally, I'm just going to compare. I'm going to say, well, is g to the xy equal to g to the u? If it is, then you probably gave me the private key that was agreed upon by the two parties. If it isn't, you probably gave me a random integer. Similarly for square DDH. While we can see that solving the discrete log is enough, there's still a question to be asked, which is there a more efficient algorithm which doesn't need to solve the discrete log? If I can solve the discrete log in, for instance, t queries, is there an algorithm for DDH which is able to distinguish in less than t queries? And in fact, the answer to this question is no. All of these three problems are equivalent in the generic group model, and there was a type bound given on all three of them at the same time in 1997. Generally, we're going to assume that we make some t queries to the generic group oracle, or we make t group operations. If we always want to be able to win in any of these three problems, t needs to be at least square root n. If we allow some loss and we want to always succeed with at least probability epsilon, then we can see that epsilon must be of the order t squared over n. In this case, what's being said here is not only that the discrete log can be solved in this time. In this case, what's being said here is not only that the discrete log can be solved in this many group operations, but both the DDH problem and the square DDH problem can be solved for in square root n queries. Okay, in the generic group model, the discrete log problem is the fastest way to solve both the square DDH problem and the DDH problem itself. But what if we allow algorithms some sort of pre-computed advice table? This is a common technique that we see when looking at, for instance, collision-resistant hash functions, where so-called rainbow tables allow you to simply look up challenges as they come in and answer them in constant time, where previously you would have had to perform the birthday attack. The question is then, okay, let's allow computing advice in this setting. So as you can see here, discrete log, well, okay, what are we going to do? We're going to say, okay, g to the a has discrete log a, g to the b has discrete log b, g to the c has discrete log c. And we're going to do something like this for as many discrete logs as we want. Now, the question is going to be, is this useful and does this help? Can we solve some online challenge faster? Well, I mean, in this case, the challenge is g to the b, and g to the b is in my table, so I'm allowed to just say b. I don't have to make any group operations, I know the answer. And in fact, not only is this true, we can in fact beat the optimal GGM bound in this setting by allowing the size of the advice table to grow up to cube root n, for instance. In the original setting, we needed at least square root n queries per challenge, but now if I have a cube root n sized table, I only need a cube root n online group operations in order to always beat the challenge that I'm given. This is clearly better than the original bound, and as the size S grows, as you can see on the right, as S grows, we're able to perform less online computations. And in fact, generally in this setting, what we care about is the so-called time-space trade-off, which is what you see on the right here. The time-space trade-off basically says, for every bit of advice that I give you, how many less queries can you perform per challenge? And in this case, the answer is, for instance, if epsilon is equal to 1, and I say I want to always invert the challenge, st squared has to be of the order n.
Alright, so that's what we have in the preprocessing setting for the discrete log problem, but what about the DDH and square DDH problems? Well, prior to our work, this was the state of the art. Now what you're looking at here is all of the previously known security bounds and attacks for the three problems that we're discussing. On the top, you see the security bounds. On the bottom, the attacks. Now, what you'll notice looking here is that on left and right, the square DDH and discrete log problems both had tight bounds prior to our work. What's interesting, however, is that these bounds no longer match. Whereas in the traditional GGM setting, the discrete log and square DDH problems had an equivalent bound. Now, in the preprocessing setting, there's a faster attack for square DDH than simply inverting the discrete log. Prior to our work, it was unknown whether there was an equivalent attack that could be applied in the DDH case. That is to say, the prior known attack for DDH in the preprocessing setting was still inverting the discrete log. However, the prior known security bound matched that of square DDH, leaving open the possibility that there was in fact a better attack. Now, let's move on to discuss the results. Our main research question is DDH still equivalent to discrete log even with preprocessing? And the answer is a resounding yes. This is the current state of the art as of our new work. Notice that previously the DDH problem had a different security bound and attack, but now in our work we've proved that in fact the tight bound for the DDH problem matches that for the discrete log. That is to say, preprocessing does not allow us to solve DDH any faster than the discrete log. This is different from the case of the square DDH problem, where preprocessing does in fact grant some extra advantage which is possible over discrete log. As a byproduct of this result, we additionally prove what's known as a K-XOR lemma for the DDH problem itself. In the K-XOR problem, you're given K independently sampled instances of the DDH problem, and you're expected to output the parity of all of the individual challenge bits. That is to say, in the DDH problem, if you're given G, G to the X, G to the Y, and G to the U, where U is either equivalent to Z or XY, and you're expected to output 1 if it's Z and 0 if it's XY, now we're given K instances, X1, Y1, U1, up to XK, YK, UK, and we're expected to output the XOR of all of the bits B1 through BK. Now, there's clearly a trivial attack where we simply solve each instance independently. The question is, can we beat such an algorithm? And the answer is yes. The multi-discrete log problem can be solved slightly faster than this trivial bound, as there is now a K inside the bound. That is to say, when given multiple instances of the discrete log problem, there is some speed up compared to solving each independent instance separately. The question then is, can we beat the multi-discrete log problem in the DDH setting? And the answer is a resounding no. Our bound shows that the multi-discrete log problem is also tight for the K-XOR problem. That is to say, in all three settings, GGM, auxiliary input or preprocessing, and the K-XOR setting, the decisional Diffie-Hellman problem is equivalent to the equivalent model's discrete log problem. With the main results presented, let's get into some of the technical details. Of course, for full techniques and all of the proofs, I encourage you to read the full paper. Our main proof follows in 3 stages. As a short overview, we're going to start in the preprocessing setting, move to the K-XOR setting. From the K-XOR setting, we're going to move again to something known as the hyperplane DDH setting. And finally, in the hyperplane DDH setting, we're going to prove our main lower bound. I'll introduce shortly what the hyperplane DDH setting really is. Additionally, as we move between the preprocessing setting, the KXOR setting, and the hyperplane DDH setting, the bounds on our advantage are going to change, as well as the query complexity. At the end of the day, the bounds that we prove in the hyperplane setting are good enough that they imply both the new bound for SXOR and the KXOR lemma, as well as the main preprocessing result. The first reduction in our proof is relatively simple. Here, we're given access to a preprocessing algorithm denoted A1 and A2, where A1 is some unbounded algorithm outputting an S-bit advice string, and A2 is some online algorithm making T queries to a generic group oracle. This algorithm that we're designing takes as input S independently sampled DDH instances in the GGM model, as well as access to a GGM oracle. Now, what this algorithm is actually going to do is relatively simple. First, this algorithm is going to randomly sample an advice string. Now, clearly, with probability 1 over 2 to the s, this value would match the value output by A1, or the offline preprocessing algorithm that we're given access to. Now, all that we're going to do is we're going to pass each of the S independent instances along with the guessed advice string to A2 and have it run as if it were given the output to A1. Finally, we're going to output the XOR of all the bits output by each of the independent instances of A2. Now, if we look at the number of queries as well as the advantage of this algorithm, we'll notice that while the original algorithm made T queries, because the new algorithm needs to run the original online algorithm S times, it's going to make ST queries. Similarly, for the advantage, because we need to guess the advice string, there's going to be some 2 to the s loss on the original advantage. However, importantly, if we guess the proper advice string, we will still be able to achieve the epsilon advantage of A2 on each of the instances, thus giving us this epsilon to the s advantage. Now, I'm leaving out some of the technical details, but intuitively, all the algorithm is doing is guessing an advice string and then computing independently as if it were the actual advice string output by the preprocessing algorithm. In this way, we're able to transform any auxiliary input or preprocessing DDH algorithm into an S XOR algorithm, where S is the length of the advice string. Next, I'm going to take a short aside to introduce the hyperplane query model, which was introduced in 2015 to address the multiple discrete log problem, and we've extended to address the DDH problem, specifically the KXOR DDH problem. In this model, there's some hidden vector which is placed inside of an oracle. An algorithm in this model asks hyperplane queries to the oracle, and the oracle will simply respond whether or not the hidden vector lies in the hyperplane that the algorithm queried. The goal of an algorithm in this model is to output at the end the value of the hidden vector. The intuition behind why this model would be useful when looking at generic group algorithms is that by making queries to a generic group oracle, I can write effectively linear relationships between the initial values that I'm given. For instance, if I'm given sigma x and sigma y, I can compute sigma x plus y, or any constant times x plus any constant times y. Similarly, in this model, we're able to ask any linear equation of this form and determine whether or not the hidden vector lies in such an equation. With that introduction out of the way, I'm going to move on and introduce the second reduction. The second reduction that we do is going to now take the S XOR algorithm that we generated in the last stage, or now any S XOR algorithm, and it's going to simulate it using only these new hyperplane queries in order to recover the hidden vector within the hyperplane oracle. Here, intuitively, we're really performing some type of lazy sampling, except that we're doing it with these hyperplane queries. Whereas previously, when I'm lazy sampling, I may look at a value of a function, for instance, sigma in this case, and I say, okay, every time you query some location, if I haven't sampled it before, I simply sample a unique random value and give it back to you. Now, there's one additional piece of information, which is what the actual discrete log value corresponds to. Notice in this table, when we're simulating the SXOR input, we're simply finding the image of all of the various basis vectors that would have been given to the SXOR algorithm itself. In such a way, we're somehow able to set up these hyperplanes, and then every time the SXOR algorithm would make a query, we use hyperplane queries to simulate how that query would actually function. Here, the real intuition is to understand that the discrete log of the labels given to the SXOR algorithm are actually just the hyperplanes that we're asking the oracle. Every time I need to lazily sample a new value, I have to ensure that it is in fact a unique value, and to do that, I need to search through the previous values that I've seen. As such, I'm able to lazily sample a label function with only a quadratic number of queries. As you can see in the bottom left, the number of queries goes up quadratically, where S here corresponds to the size of the simulated input, and ST corresponds to the number of online queries. The advantage of this new algorithm is going to be exactly the same because fundamentally, in the hyperplane model and the GGM model, we're really somehow doing the same thing. The only difference is, instead of being given the input vectors as a challenge, the input is now hidden inside the oracle. Finally, the last part of our proof is the actual lower bound, which we prove in the hyperplane model. In order to prove this lower bound, we're going to view the hyperplane algorithm as a decision tree where each query asked is either going to determine we're going to go left or we're going to go right. That is, which subtree we're going to proceed to. If you look at the right, all of the vertices labeled with green are the cases where the hyperplane that was asked at the node does contain the hidden point. Similarly, the red paths are those where the hyperplane does not contain the hidden point. Importantly, what we do in this step is we consider the advantage of an algorithm over the full tree. That is to say, the whole tree has some inherent advantage solving for k independent instances using q queries, where q is the depth of the tree. What we're able to show by viewing this as a decision tree is we're able to split up the advantage into the left-hand subtree and 2 copies of the right-hand subtree with an extra query. However, importantly, as you can see here, when we move to the right-hand subtree, we're additionally getting rid of one of the independent instances. That is to say, if an algorithm is able to guess a hyperplane which contains the hidden point, we are revealing the value of an entire instance. Luckily, however, this is enough, and the induction is still able to go through. Fundamentally, the intuition behind our proof is that a single hyperplane query, in most cases, is able to reveal information about, at most, one instance. That is to say, it's very unlikely that any hyperplane query made by the algorithm reveals information about any further instances, which somehow limits the amount of speedup possible, despite the fact that we have multiple instances at once. Here, we end up proving this bound, where here, q is the number of queries, or the depth of the tree on the right, and s is the number of instances. Finally, in order to summarize, here are some previously open problems which we address. First, and most importantly, we prove a new, tight preprocessing bound for decisional Diffie-Hellman. That is to say, decisional Diffie-Hellman is equivalent to discrete log even in the preprocessing setting. Second of all, we prove a new, tight k-XOR lemma for decisional Diffie-Hellman. Specifically, while there is some speedup similarly to the multiple discrete log problem, the DDH problem does in fact scale when the number of independent instances is increased. Finally, this is the first paper to apply the hyperplane model to a decision problem. Previously, it had only been applied to search problems. And so that's going to be the end of the talk. I hope you enjoyed it, and of course we have a paper, and of course there's a paper to go along with it. If any of the techniques or any of the results seem interesting to you, feel free to read the paper, and that'll be all. I've been Tyler.